Hello everyone, I am Amlan Datta, and in this series of videos I am going to walk you through the fantastic world of cones and conics. This would be a three-part video where we would be discussing about conic sections for senior secondary level of CBSE and ISC boards. In this part, we would discuss about cones and conics in general form and ellipse. In the upcoming second part, we would discuss parabola, and in the third part about hyperbola, and of course some bonus tips and tricks for solving entrance level exams. So without any further ado, let's jump into the video. And by the way, thanks for tuning in to my channel. So let's first have a look at cones. Cones are primarily pyramids with a circular base. There are several ways to form a cone, but here I will show you how a double-napped cone is formed by revolving a straight line around a point. As you can see, when two straight lines intersect at a point, one of which is perpendicular to the base and the other inclined at an angle alpha from the perpendicular line, and then rotated through that point of intersection, then the solid of revolution is called a cone. If the oblique line extends the point of intersection, then two cones are formed, which is called a double-napped cone. The rotating line is called the generator. The point of intersection is called the apex. The red baseline is called the directrix, and the green center line is called the axis of the cone. If this axis is perpendicular to the base of the cone, then the cone is said to be a right circular cone. Of course, there are other types of cones such as oblique cones, which are out of scope for today's topic. So we will be discussing only right circular cones and their sections. The intersection of a plane at various angles with this cone gives us our curves, that is conic sections. When the plane is perpendicular to the axis or parallel to the base, the intersecting curve is a circle. When the plane is more than alpha, that is the angle of intersection of the lines, and cuts all the generators, we get an ellipse. When the plane is parallel to the generators and cuts the axis and the base, we get a parabola. And when the plane is parallel to the axis and cuts both the curves, we get a hyperbola. So here are the four shapes of our conic sections: circle, ellipse, parabola, and hyperbola. Now we will move towards the mathematical aspect of the conic sections and discuss some of their properties. Any conic is defined as the locus of a point whose ratio between the distance from a fixed point and the perpendicular distance from a fixed line is always constant. You can see this here. This is the fixed line and this is the fixed point. The fixed point is called the focus and the fixed line is called the directrix. If P be any point on an individual curve, then the distance Fp upon Qp will always be same for any point on this curve. This ratio is known as eccentricity. Eccentricity for ellipse is always less than 1. Eccentricity for circle is equal to 0. Eccentricity for parabola is equal to 1 and for hyperbola it's greater than 1. General form of equation of any conic section. Any conic can be represented by this quadratic equation ax square plus cy square plus dx plus ey plus f equals 0. Circles, ellipse, hyperbola, parabola can be represented by this equation. Now I will tell you, just by looking at the equation of any conic section, you can tell how you can tell that this equation is of which section. First of all, you have to ask 3 questions in this sequence. Number 1. Are both variables squared? If in this equation both the variables x and y are squared, then it is not the equation of a parabola. If only one variable is squared, then it's definitely the equation of a parabola. If both the terms, both the variables are squared, then you have to go to next question. Do the squared terms have opposite signs? If x squared and y squared have opposite signs, then it's definitely an equation of a hyperbola. If not, then go to the third question. Are the squared terms multiplied by the same number? If x squared and y squared have same coefficient, then it's the equation of a circle. If not, then it's the equation of an ellipse. Now let's see some examples of our test to determine what these equations represent in conics. Example 1. 3x square plus 3y square minus 6x plus 9y minus 14 equals 0. What was our first condition? If x square and y square are present in the equation. If they are, then it cannot be the equation of a parabola. Hence, this is not the equation of a parabola. What was our second condition? If the square terms have opposite signs. No, they do not have. Hence, it is also not the equation of a hyperbola. This equation satisfies our third condition, that the squared variables have same coefficient. that is 3 in this case. Hence, this equation is of a circle. Now let's look at the second example. 6x squared plus 12x minus y plus 15 equals 0. This equation satisfies the first condition, that is, only one term of the squared variable is present. Hence, this is an example of this is an equation of a parabola. In the third example, both the variables have squared terms. Hence, this is not parabola. Both the variables have same signs. Hence, this is not hyperbola. Both the variables do not have same coefficient. Hence, this is an equation of an ellipse. In the fourth equation, both the variables have square terms, have opposite signs, and both the variables are present here. That means it is an example of a hyperbola. The standard form of an ellipse whose center lies at any point hk, length of the major axis is 2a and the length of the minor axis is 2b, where a is greater than b, is given by x minus h whole square upon a square plus y minus k whole square upon b square equals 1. When a is greater than b and a is the denominator of x, then this ellipse is horizontal. And the reverse occurs when b is the denominator of x and a is the denominator of y. Still a is greater than b, then the major axis is vertical. Finding the coordinates of the foci of an ellipse. In this equation, a square equals b square plus c square. A is half the length of major axis, b is half the length of minor axis, and c is the distance of the focus from the center of the ellipse. If O1, that is the origin or center of the ellipse, is at hk, then F1, that is one of the focus of the ellipse, would be at h minus c comma k, and the other focus F2 would be at h plus c comma k when the ellipse is horizontal. Remember that. And when the ellipse is vertical, then the focus F1 would be at h comma k plus c and F2 would be at h comma k minus c. To calculate the length of the latus rectum, that is the straight line which is perpendicular to the major axis and passing through the focus to the ellipse, would be 2b square upon a when a is greater than b, that is when the ellipse is horizontal, and when b is greater than a, that is when the ellipse is vertical, the latus rectum would be equal to 2a square upon b. Now let us solve a problem involving ellipse. The equation of the ellipse is given by 4x squared plus 9y square equals 36. We have to find the coordinates of the foci, major and minor axis, eccentricity, latus rectum, and its vertices. We have to change this equation in the standard form of x minus h square upon a square plus y minus k square upon b square equals 1. Dividing both the sides with 36, we get this equation, and further solving it, we get x square upon 9 plus y square upon 4 equals 1. Now this is the standard form of the equation where h and k are both 0. That means the ellipse has its center at the origin. This is the drawing. This is the center of the ellipse, this is one focus, and this is the other focus, and we have to find the coordinates of the focus. Now how do we find the coordinates of the focus? By this equation. A square equals b square plus c square, where a square is half the length of the major axis, b square is the half the length of the minor axis, and c square is the distance of the focus from the center. A square is 9, b square is 4, so c square equals a square minus 4, that is 5, and hence c equals root 5. So f1 would be equal to h minus c comma k, that is minus root of 5 comma 0, and f2 would be h plus c comma k, that is root of 5 0. Major axis equals 2a. If a square equals 9, then a would be equal to 3, and major axis is given by 2a. So 3 to the 6, it comes out to be 6, and minor axis is 2b, that comes out to be 4. Eccentricity is given by c upon a. c is root over 5 and a is 3, hence eccentricity is root 5 by 3. Latus rectum, since this ellipse is horizontal, the latus rectum formula would be 2b square upon a, which comes out to be 8 upon 3.